Chapter 1.10.12 Node-pressure Eviction. Summary. Node-pressure eviction * is a feature where the kubelet ends pods preemptively to manage resource use. It monitors node resources like memory and disk space, using eviction thresholds to make decisions without considering pod priorities or disruption budgets. Pod termination is immediate or after a configured grace period. The kubelet attempts to free resources by removing unused images before terminating pods. For managed or static pods, new ones replace those evicted based on priority. Different parameters, signals, and thresholds aid eviction decisions, and priority influences eviction order. Threshold configurations include soft and hard settings, with hard terminating immediately. Multiple file systems help organize various data layers, making node management efficient. Node-pressure eviction. Node-pressure eviction allows the kubelet to terminate pods to free resources when usage is high. This feature is available in Kubernetes version 1.31 by default. The split image file system feature introduces new eviction signals and metrics. Enabling kubelet separate disk GC is needed to use container-fs in version 1.31. Only CRE OV 1.29 Plus supports container-fs, allowing the kubelet to monitor node resources like memory and disk space. Node-pressure eviction differs from API-initiated eviction and ignores pod disruption budget and termination grace period seconds settings. With soft eviction thresholds, configured grace periods are respected. Hard thresholds use a 0-second grace period, terminating immediately. Self-healing behavior. The kubelet tries to free resources on a node before terminating end-user pods. It may delete unused container images if disk space is low. For pods managed by workload objects like stateful set, the control plane creates new ones to replace any evicted due to resource issues. If a static pod is evicted under resource pressure, the kubelet will attempt to restart it, accounting for its priority level. High-priority static pods are favored when resources are limited, but the kubelet continues trying to run all static pods. Eviction signals and thresholds. The kubelet manages resource allocations in Kubernetes and makes decisions about evicting pods based on various parameters. One key concept includes the eviction signals, which represent the current state of resources and are used to determine if resources are low by comparing them against predefined eviction thresholds. The thresholds define the minimum amount of a resource that should be available on a node, and the kubelet uses these thresholds alongside signals to decide when to perform evictions. Memory and file system signals. * On Linux nodes, memory signals are derived from C group FS rather than tools like FreeM, ensuring resource decisions are accurately reflective of container environments. Windows nodes use the global memory commit levels to compute available memory. The kubelet also monitors several file system identifiers like NodeIFS, ImageFS, and ContainerFS to assess the system's storage resources. These signals are essential for making informed eviction decisions under resource constraints. File system configuration. * NodeIFS refers to the main file system on a node, including essential directories and volumes not backed by memory. ImageFS is for container images and optional writing layers, providing a separate area from the main file system. ContainerFS may combine these features on root or separate storage, creating flexibility in resource management. The kubelet uses these configurations to auto-discover file systems to determine resource allocation effectively. Deviations from these configurations are not currently supported, imposing limitations on administrators. Eviction thresholds. * The kubelet allows defining custom eviction thresholds that dictate when pods will be evicted, including both soft and hard levels. Soft thresholds require a grace period before taking effect, providing a buffer for administrators, while hard thresholds prompt immediate evictions when limits are reached. Soft eviction thresholds. Asterisk. Users can configure soft thresholds with specific grace periods, which delay the eviction process until the grace period lapses. There's flexibility to define a maximum grace period, ensuring a balanced allocation between administrative control and resource necessity. Custom configurations are strengthened with the use of flags to precisely control eviction behavior, though limited adjustments can apply depending on current variables. Hard eviction thresholds and defaults. Asterisk. Hard thresholds initiate immediate action without grace periods if resources hit critical lows, allowing rapid resource recovery. Kubelet has default hard thresholds set unless explicitly overridden, dictating strict control over minimum system resource availability. Separate configurations for container thresholds aren't supported yet, highlighting some limitations in custom threshold settings and offering specific default adjustments. Eviction monitoring interval. The kubelet checks eviction limits every 10 seconds based on its default housekeeping interval. Node conditions. The provided code snippet is a YAML configuration for the kubelet, specifying hard eviction thresholds for memory, node file system availability, and image file system availability. The thresholds set are 500 MB for memory available, 1 GB for node file system available, and 100 GB for image file system available. Additionally, it specifies minimum resources to be reclaimed before eviction, which are 0 MB for memory, 500 MB for node file system, and 2 GB for image file system. The *kubelet*** is a crucial component of managing node resources in a Kubernetes cluster. When a node is under pressure, possibly due to a hard or soft eviction threshold being met, the kubelet updates node conditions. These conditions are then represented in the control plane as taints, enabling the system to manage resource allocation by influencing scheduling. The frequency of these updates can be configured, but the default is every 10 seconds. Node condition oscillation * can be problematic when nodes hover around soft eviction thresholds, fluctuating between true and false states, leading to inefficient eviction decisions. An * eviction pressure transition period * flag can be used to manage these transitions, with a standard period of 5 minutes, to stabilize the node's assessed condition. Before evicting pods, kubelet attempts to * reclaim resources * by managing space on various file systems. In instances where * disk pressure * is felt, the kubelet prioritizes freeing disk space by deleting unnecessary files, images, and dead pods. The order and type of reclamation efforts depend on the file systems in use, which can include Node-ifs, image.fs, and container.fs. Should resource reclamation prove insufficient, *pod eviction * is initiated. The kubelet determines which pods to evict based on resource usage, priorities, and requests. Generally, best effort or burstable pods where usage exceeds requests are likely candidates for eviction, while guaranteed pods, with precisely defined requests and limits, are minimally impacted. The priority of pods becomes a critical factor during evictions induced by inode or process ID starvation. File system-specific pod sorting * ensures evictions are handled according to the specific triggering event on the file system. This depends on whether the node uses a shared or separate configuration for Node-ifs, image.fs, and container.fs. It determines the focus of reclaim actions, either on volume, logs, writable layers, or image storage, to reduce node pressure effectively. To prevent repetitive evictions without substantial resource reclamation, kubelet can be configured through the * eviction minimum reclaim * flag to reclaim a minimum set amount of resources. This ensures resources are adequately managed before more evictions are triggered by reevaluated thresholds. This, however, has default settings of 0 across resources unless explicitly changed, impacting node stability and efficiency. Node out-of-memory behavior. If a node runs out of memory before the kubelet can reclaim some, the node relies on _killer. To fix the issue, the kubelet assigns _score_ag to containers based on their codes. The _score_ag value helps _killer determine which container to terminate by assessing the percentage of memory each uses and adjusting the score accordingly. Containers with high scores are more likely to be killed. Containers within low cos pods that exceed memory usage limits are first to be killed. Despite being killed, affected containers can be restarted by the kubelet following the restart policy. Good practices. The code sets a hard eviction threshold for memory availability at 500 MB, meaning pods will be immediately terminated if memory falls below this level. It also reserves 1.5 GB of memory for system processes to prevent them from impacting the overall node stability. Configuring eviction policies is essential to manage resource allocation in Kubernetes effectively. By using proper scheduling strategies, such as reserving a certain percentage of memory for system daemons and setting eviction thresholds, you can prevent premature pod evictions due to memory pressure. In a scenario where node memory is 10 GB, it's recommended to reserve 1.5 GB for systems with system reserved configuration and enforce evictions at 95% utilization. This ensures efficient utilization and prevents the system from encountering out-of-memory errors. Proper eviction strategies help in managing memory effectively. In the given scenario with a 10 GB memory node, 10% is reserved for system usage, and pods must not utilize more than 95% collectively to avoid system issues. The kubelet uses system reserved flag to allocate 1.5 GB memory for smoother operations. Activation of the eviction threshold occurs if pods use more than their limit or system memory exceeds 1 GB, causing memory available to drop below 500 MB, triggering evictions. When configuring daemon sets with eviction policies, pod priority plays a crucial role. Assign a high priority to daemon sets using priority class name to prevent such pods from being evicted during node pressure. Alternatively, use lower priorities for pods that should only run when excess resources are available. This ensures crucial daemon set pods maintain operation even during resource strain while managing less critical pod operations effectively. Known issues. Kubelet may not detect memory issues quickly because it checks memory usage at regular intervals. If memory rises rapidly, the killer may get triggered. Use the kernel memcg notification flag to alert the kubelet immediately. To prevent memory pressure issues without extreme utilization, you can use the kube reserved and system reserved flags to allocate specific memory for the system. The Linux kernel tracks active file-backed memory, which kubelet cannot reclaim. Heavy local storage use may show as high resource use, leading to node memory pressure and potential pod evictions. Active file memory is considered high resource use and can mistakenly trigger pod eviction due to pressure. This can occur if kernel block buffers are numerous on the active LRU list. To handle intensive I/O workloads, set memory limits and requests equal for containers and estimate the optimal memory limit adequately.